In this module, I briefly want to talk about the practical issues you might encounter when you're working with flip-flops. So the first thing that you'll see here is a flip-flop that's connected to a clock through a gate, an AND gate in this case. And basically this is a terrible idea. Okay, so essentially never put a logic gate between the clock and the flip-flops. And I think many of you will find that sometimes in the lab you'll be tempted to do this, but it's basically just not a good idea. And the reason it's not a good idea is sort of shown in this timing diagram at the bottom. So if you ask, so C here is the actual clock signal that's sensed by the flip-flop, so it's the flip-flop's responding to the edge, the positive edge of C. And you can just ask, what is C? Well, it's the AND of this enable input and the actual clock signal. And of course, C is going to be high only if both the clock and enable are high, which is the case over here. And then it will be stay low. It will go up here following this little blip in the enable signal. And then again at this point. And I think that's it. And so just looking at this trace, you can see that this is a very non-periodic signal, and obviously this particular flip-flop will be completely out of sync with the rest of the circuit, and this is very likely to create issues. Okay, the second sort of issue you have to think about, the reality is somehow what should the clock period actually be given the system you're trying to build? And the answer, the first part of the answer is actually quite simple. So you just look at what the longest path in your combinational circuit is, right? And you know that the clock period should be longer than the number of gate delays that you have, or the sort of the longest path in that circuit, right? So in this particular example, you can see that the longest path is somewhere from this gate, 2, 3, 4, 5. So you have a path that sort of goes through here that takes 5 gate delays. Similarly, could go through here. It's also 5 gate delays. And so you'd just based on that, you would say that one clock period here should be larger than 5 gate delays. Okay, I think that part of the answer is quite intuitive. But there's a little more to this, because the actual time that you need to take to compute correctly is a little bit longer. So there's 3 other times that we're going to talk about, or sort of time constants that we're going to talk about, which are the setup time, the hold time, and clock to Q. So the most intuitive of these time constants is the setup time. So what's the setup time? It's basically saying that after the combinational circuit has finished its computation, so it's settled sort of to the correct final value, just add a little bit of time before the clock edge. Okay, so that's T setup, and obviously T setup adds to the critical path. So you could sort of say it's so here's T setup. So time after the combinational circuit has completed to the actual clock edge, it's sort of a safety buffer. And this adds to critical path at the end. Then the other time constant that's relatively intuitive is clock to Q. So it's basically here. Clock to Q. So what is that? That's basically saying that after the clock edge, you want to hold the old value of the output Q for the old value of the output Q will be held for some time. Okay, so it's basically just an intrinsic property of the flip-flop that the Q doesn't change immediately. So you kind of need to wait for the Q to actually settle a little bit, and of course only once the Q has settled to its new value can the combinational circuit start over and produce the correct output. So clock to Q adds to the critical path in the beginning. So adds to critical path in the beginning. Okay. So both T setup and clock to Q add to the critical path, one at the end, one at the beginning. Now the third time constant that we're talking here is T hold. Okay, so the hold time essentially says that the value of the D input will need to be stable a little bit after the clock edge. Okay, so that actually doesn't affect the critical path at all, because the input we're not going to look at the input essentially up to the next clock edge. So as long as T hold is short compared to the critical path, that's perfectly fine. But what it does do is says that there can't be any path that is extremely short. So here the shortest path in the system is essentially this path here, right? So it would have one gate delay from the output to the input. And you could imagine if this was a very short path, then the input D might change more quickly than is sort of compatible with this particular the intrinsic sort of mechanics of the flip-flop. And so that's what essentially T hold says. It says there can't be a short path in the system. So let me write that here. So T hold says don't have too short a path. Okay, so that's sort of three intrinsic time constants. They're a little bit different for every particular type of flip-flop, but they're always there, and you have to sort of take them into account when determining what the correct clock period should be. Good, so this is just summarizing this again. So T setup, the amount of time that D, the data input, must be stable before the clock edge, and that adds to the critical path. The clock to Q is a time from clock edge to Q changing, and again it adds to the critical path. And T hold is the time D must be stable after the clock edge, and this sets a minimum path from Q of one flip-flop to the D, the input to another, or the same one. Okay, so the third thing you need to consider, and again this is something you're actually going to see, have to think about and see in the lab, is the fact that flip-flops are hooked up, or your system is hooked up to external inputs, and the external inputs cannot be synchronized to the clock. So the keystrokes on your keyboard are not synchronized with the internal workings of your system. And one thing that can happen is that your data input, your external input, changes together with the clock edge. And when that happens, the output Q might settle into some sort of metastable state. So it could get caught at some intermediate value. It eventually go to either 0 or 1, but this process could take some amount of time. And during that time, the value of Q is sort of undetermined. So you can really think of this as sort of being a metastable state, where you have at sort of the state Q of your flip-flop. Over here you have the logic 0, here's the logic 1, but for some amount of time you might get stuck at this intermediate value that's sort of meaningless for your system and actually might generate errors. And so the question is simply, you can't avoid this, but the question is, how do you deal with it? Okay, so again, what do you do to deal with this? So as we just saw, if you just have a single flip-flop, an external input, and then an output, this output can be metastable. It can take some sort of random value, which has no meaning or no well-defined meaning to your system. So, could you come up with a good solution to this problem? Well, let's first consider the 2D flip-flop in parallel. Would this actually somehow help you deal with this? And the answer, I think, is pretty obviously that this is not a good idea. Why is that? Because now you essentially, instead of just having one flip-flop where the output may take a metastable value, you actually have two flip-flops where the outputs might take different potentially metastable values, and that could, in fact, create more errors. Instead, I think this is a good idea, namely to take two flip-flops and put them in series. And the reason this is a good idea is because you're kind of building in, essentially you're building in a delay. Like if you're stuck, if that first flip-flop is stuck in a metastable state, it will eventually settle to either a 0 or a 1. It's metastable after all, right? And this will essentially happen with some, the longer you wait, the more likely it is to happen. And by just putting in this second flip-flop, you're essentially enforcing that whatever output is on cue will have to wait there for one whole clock period before it gets read into the next flip-flop and then eventually into your system. And so just by putting in this time delay, essentially you let the output settle into a pure value, and you're kind of more or less avoiding the issue of metastability.